In this video, we'll be talking about rational functions. So first up, let's see what form that we see rational functions in. Rational functions are written in the form f of x equals to p of x divided by q of x, where p of x and q of x are polynomial functions, where q of x cannot be 0. So rational functions will oftentimes have what are called asymptotes. There are 3 types of asymptotes: vertical asymptotes, horizontal asymptotes, and oblique or slanted asymptotes. So first going to look at vertical asymptotes. Vertical asymptotes are values that make the denominator equal to 0. One thing we have to note though is if x is equal to a is a common 0 for both the numerator and the denominator of the function, then there is no vertical asymptote at that x equals a. Instead, there's a hole in that graph, because if we had the same common 0 on both top and bottom, they would effectively cancel out or be removed, and that removal will create a hole in the graph. So let's look at some examples here on how to find vertical asymptotes of rational functions. For number 1 here, we have f of x equals to x plus 1 divided by 4x plus 12. So first thing we do is we would find vertical asymptote. We do that by just setting the denominator equal to 0, and we want to solve for x. So our denominator here is 4x plus 12. So we set that equal to 0. So we solve for x, we subtract 12 over. So it gives us 4x equals negative 12. And then we divide both sides by 4. So x equals to negative 3. So our vertical asymptote, denoted as VA, will just be x equals to negative 3. Every time you write any type of asymptote, they have to be in equation form. So vertical asymptotes would always be x equals to our term. So our vertical asymptote here is x equals negative 3. Now let's look at number 2 here on the right. So we have f of x equals to x squared plus 7x plus 10 divided by x squared minus x minus 6. So whenever we see a rational function written with polynomials like this, if you look at each polynomial separately, they're actually quadratic polynomials. So we always want to factor them first before we do anything. So if we rewrite this rational function with factored forms, we have x squared plus 7x plus 10. So two numbers that multiply get you 10, but add to get you 7 would be x plus 2 and x plus 5. So that's the factor form of the top. Now let's look at the factor form of the bottom. X squared minus x minus 6. So two numbers that multiply get you negative 6, but add to get you negative 1. That would have to be 3 and 2, but specifically it has to be x plus 2 and x minus 3. But you notice again, we have the same term x plus 2 on top and bottom. So our common term, first off, is let's find our vertical asymptote. First, vertical asymptote, set the bottom equal to 0 and solve for x. So because it's in factor form already, we just set both of them separately equal to 0. So that gives us x equals negative 2 and x equals 3. However, x equals negative 2 would not be a vertical asymptote because there's an x negative 2 on top as well. X equals negative 2 on top in the form of x plus 2. Because they cancel each other out, there will be a hole there. So this would create a hole at x equals negative 2. So our only vertical asymptote here would just be x equals 3. Now we look at horizontal and oblique asymptotes. So for horizontal asymptotes, the graph of a rational function has a horizontal asymptote if the degree of the numerator and denominator are equal, or if the degree of the denominator is greater than the degree of the numerator. Now for oblique asymptotes, the graph of a rational function has an oblique asymptote if the degree of the numerator is 1 more than the degree of the denominator. So we'll look at more examples of that later. So now we move on to how to find horizontal or oblique asymptotes. So if the degree of the denominator is greater than the degree of the numerator, the line y equals to 0 will be your horizontal asymptote. If the numerator and denominator have the same degree, the line y equals to a sub n over b sub n is your horizontal asymptote, where a sub n is the leading coefficient of the numerator, and b sub n is the leading coefficient of the denominator. And finally, if the degree of the numerator is 1 more than the degree of the denominator, then the line y equals to mx plus b is an oblique asymptote of the graph. Now, to determine the equation of oblique asymptote, you want to divide the polynomials, and quotient is the equation of the oblique asymptote. That can be done by using synthetic division. So those are the 3 ways in how to find horizontal or oblique asymptotes. So let's look at some examples. So for each function, determine if there is a horizontal or oblique asymptote and give the equations of the asymptotes. For number 1 here, we're looking at f of x equals to 2 divided by 5x minus 15. So right away, we notice that our denominator has a higher power than our numerator. So right away, we know we're going to have a horizontal asymptote. And then automatically, because our denominator, the leading power of our denominator is greater than the numerator, then automatically we know our horizontal asymptote is going to be y equals 0. Because there's a horizontal asymptote, there is no oblique asymptote. Now for number 2, f of x equals x plus 1 divided by 4x plus 12. So first things first, always look at our leading terms. So our leading term on the numerator is x, and our leading term on our denominator is 4x. Both leading terms have the same power, so we know right away our horizontal asymptote is going to be just focusing on the leading term on top and bottom. So we know it'll be y equals to x over 4x, but we just look at our coefficients here. So just be 1 over 4. So we only have a horizontal asymptote of y equals to 1/4 for number 2. So for number 3 here, we have f of x equals 2x squared plus 3x divided by 2x minus 5. So first, again, we look at our leading terms. In our numerator, we have 2x squared. In our denominator, we have 2x. So obviously we see that our numerator, the leading term in numerator, is greater than the leading term in our denominator. So there would be no horizontal asymptote, right? But there would be an oblique asymptote because the leading term on the numerator is only greater than the denominator by 1, by a power of 1. So to find oblique asymptote, what we do is we would use division. We could actually use synthetic division if we wanted to, but let's actually do long division in this case. So long division, we put our 2x squared plus 3x on the inside here of our division, and the 2x minus 5 on the outside. So to divide, we find out how many 2x's can fit into 2x squared. That would actually just be an x amount. So if we multiply 2x times x gets us 2x squared, but also x times negative 5 gets us negative 5x. So if we subtract that, this first term is 0. Negative is actually a positive 5x, so that gives us 8x. So now how many 2x's can go into 8x? There would be 4. So we do plus 4 on top. And then we multiply again, we get 8x. And then 4 times negative 5 is negative 20. So when we subtract, that gives us 0 for the x's, but then a 20 as our remainder here, because 20 is smaller than 2x minus 5. But we don't actually focus on the remainder, we'll only focus on our quotient here. So our oblique asymptote would just be x plus 4. And remember that oblique asymptote is always in mx plus b form. It's consisted of a linear equation. So now kind of putting everything together, we can now graph a rational function. So there's some steps to do so. So step 1 is, if possible, simplify the rational function. So it means by factoring or something like that. Next step is find the vertical asymptotes by solving our q of x, our denominator, equal to 0. Number 3 is finding any horizontal or oblique asymptotes. Then we want to find x-intercepts if any, and then find y-intercepts, if any. Now we use test points to examine the behavior near the x-intercepts in our asymptotes, and draw a number line, mark all x-intercepts and vertical asymptotes. Then we use the test points to determine the behavior of the function in each interval, then combine everything together into a sketch. Alright, so let's look at an example on how to graph a function. In this case, we have f of x equals x squared minus 4. So the first thing we do is we want to simplify our function. So we notice on the denominator here, we have x squared minus 4. That can be factored into x plus 2, x minus 2. So we rewrite this function as x over x plus 2 times x minus 2. So first things first is to find our asymptotes. So to find our asymptotes, we would first find a vertical asymptote, set our denominator equal to 0 and solve for x. So we set x plus 2, x minus 2 equals 0. So that means we set both of them separately equals 0 because they're already in factored form. So solve for x, we get negative 2 and positive 2. So that's our vertical asymptotes. Now for horizontal, looking at our leading terms on top and bottom. So on top we have an x, on the bottom is x squared. The bottom has a higher power. So because of that case, right away our horizontal asymptote is just y equals 0. Now we look on to find x and y intercepts. To find the x-intercept, we set y equals 0 and solve for x. So when we do that, we get x over x squared, set that equal to 0, multiply both sides by the denominator, that just gives us x equals 0. So that means the point that is our x-intercept is 0, 0, which coincidentally in this case would also be our y-intercept. Because the y-intercept, you set x equals 0 and you solve for y, but we know that's going to get you 0 again. So now what we do now is we figure out our behavior on each interval of our function here. So to do so, we kind of draw a number line. And we know on the very left of our number line is negative infinity. Very right is positive infinity. And then we plot our vertical asymptote and also our x-intercept. So we know our vertical asymptotes are negative 2 and positive 2. And then we plot our x-intercept at 0. And then what we do now is we pick test points between each interval to figure out what the behavior is, if it's positive or negative. If it's positive, it means it's above the x-axis. If it's negative, it's below the x-axis. So we pick negative 3, negative 1, positive 1, and then positive 3. So we take these the x values and test them and see if we get negative or positive. So just to kind of simplify things, when you plug in negative 3 here, you get negative 3 over negative 3 squared minus 4. That's negative 3 divided by 9 minus 4. So that'll be a negative 3/5. So between the first interval, we know it's going to be a negative. Now when we test x equals negative 1, again, you can use your calculator or simplify in your head. You have negative 1 divided by negative 1 squared minus 4. That'll be negative 1 divided by negative 3, which gives you a positive 1/3. So I'll give you a positive between that interval. Now next interval between 0 and 2, we picked x equals 1. So you plug 1 in, you get 1 on top, 1 squared minus 4, that gets you a negative 3. So that's a negative number. So it's negative. And going by our trend here, we should be getting a positive in our last interval, but let's test it. So we picked positive 3. So that'd be 3 divided by 9 minus 4, because 3 squared. 9 minus 4 gives us 5. So that'd be 3/5. Again, it's positive. So what that tells us about our behavior is that between negative infinity and negative 2, it's going to be below the x-axis. Between negative 2 and 0, it's going to be above. between 0 and 2, it's going to be below again. And then finally from 2 to infinity, it's above the x-axis. So putting everything together, we're going to get this graph here. So some things to note on this graph is you see that we do have vertical asymptotes at -2 and 2. So normally it's denoted by a dotted line going all the way from top to bottom at these 2 points here. So basically the graph never actually crosses the vertical asymptotes. It just gets really, really close to it, but it kind of does a jump as it comes from left to right. And then we notice again our x and y intercept is at 0. And then finally we look at the behavior. So if we look from -3 to -2, it's below. Between -2 and 0, it's above. Between -2 or between 0 and +2, it's below again. And then finally, when you go to 2 to infinity, it's above the x-axis. And that is how we would graph a rational function. All right, so let's look at another example. Graph the function f of x equals 2x squared plus 3x divided by 2x minus 5. So first thing we do is we want to simplify our function. So we can factor out an x on top. So we have x times 2x plus 3 divided by 2x minus 5. Next step is to find our asymptotes. So let's find our vertical asymptote. Vertical asymptote, all we do is we set the denominator equals 0 and solve for x. So we add 5 and divide by 2. So we have 2x equals to 5. And divide both sides by 2, we get x equals to 5 over 2. Now, in this particular function here, there is no horizontal asymptote because our leading term on top, 2x squared, is greater than the leading term on bottom, which is 2x. So there's no horizontal asymptote. Kind of keep that in mind. But there is a there is an oblique asymptote because the leading term on top is greater than the leading term on bottom only by a power of 1. So we can find oblique asymptote by doing long division. So we write 2x squared plus 3x divided by 2x minus 5. So how many times can 2x go into 2x squared? That would be x amount of times. Multiply 2x squared, x times negative 5x, or it's negative 5x. Subtract 2x squared minus 2x squared is 0, and then 3x minus 5x gives us a positive 8x. How many times can 2x go into 8x? That would be 4 times. 4 times 2 is 8x. And then 4 times negative 5 is a negative 20. So subtract, we just get 20, which is smaller than 2x minus 5. So that's our remainder. But for that case, we only care about our quotient, the oblique asymptote. So that means that y equals to x plus 4 is our oblique asymptote. Now we need to find our x and y intercepts. So to find the x-intercept, we're setting the y equals 0 and solve for x. So it turns out to be x times 2x plus 3 divided by 2x minus 5 equals 0. Multiply both sides by our denominator. That will just give us x times 2x plus 3 equals 0. Now that they're factored, we set both of them separately equal 0. And then we know x equals 0, that's 1. The other one is we solve for x, so we subtract 3, so 2x equals to negative 3. And divide by 2 both sides, x equals to negative 3 over 2. So there, as points, our x-intercept is going to be 0, 0, and also negative 3 over 2, 0. Now, to find the y-intercept, we do the same thing. We do the opposite. We set x equals 0, solve for y, but because we know an x-intercept is 0, 0, that will also tell us that that's also our y-intercept. Okay, so now what we need to do now is we need to figure out our behavior of our function. To figure out the behavior, we plot our x values that we have on the number line. So we say negative infinity over here. Infinity, so our x's we have are the vertical asymptote, x equals 5 over 2, and the two intercepts, x-intercepts, 0 and negative 3 over 2. So we plot them, negative 3 over 2, 0, and 5 over 2. Now we pick test points in between each interval and plug into our original function. So between negative 3 and negative 3 over 2, negative 3 over 2 is negative 1.5. So we can say we pick negative 2. Between negative 1.5 and 0, we can pick negative 1. Between 0 and 5 over 2, 5 over 2 is 2.5, so we can say pick a positive 1. And from 2.5 to infinity, we can pick 3. So now we take these values, x test values, plug into our function, and see if we get positive or negative. So when x equals to negative 2, we plug it into our factor form, gets us negative 2 times 2 times negative 2 plus 3 divided by 2 times negative 2 minus 5. So if we do that real quick, we'll get 2 times negative 2 is negative 4, plus 3 is negative 1, times negative 2 is a positive 2. But in the bottom we have 2 times negative 4 is negative 4, minus 5 is negative 9. So we know for sure it's going to be a negative right here. Now, let's test when x equals to negative 1. So we plug it in. We have negative 1 times 2 times negative 1 plus 3 divided by 2 times negative 1 minus 5. So 2 times negative 1 is negative 2 plus 3 is positive 1 times negative 1 is a negative 1. And 2 times negative 1 minus 5, so that would be negative 2 minus 5, which is negative 7, which gets us positive. So let's test when x equals to positive 1. Should give us a negative, but let's plug it in just to be sure. 1 times 2 times 1 minus plus 3, I'm sorry, over 2 times 1 minus 5. So 2 plus 3 is 5 times 1 is 5 divided by 2 minus 5 is negative 3. So yeah, that would give us a negative. And lastly, when x equals to 3, so we have 3 times 2 times 3 plus 3 over 2 times 3 minus 5. So 6 plus 3 is 9, times 3 is 27, divided by 6 minus 5, which is 1. So again, it gets us positive. So what does that tell us? So the behavior is between negative infinity and negative 3 over 2, it's negative. Between negative 3 over 2 and 0, it's positive. And between 0 and 5 over 2, it's negative again. And between 5 over 2 and infinity, it becomes positive again. So our graph should look something along the lines of this. So it's kind of zoomed out because I wanted to fit everything to fit in the graph. But you'll see here is that we have a vertical asymptote around about 5 over 2. So that's somewhere right here. And then we also have an oblique asymptote at y equals x plus 4, so that'll be a slanted. So it would be something along the lines of this. So you notice basically is our graph is going to be squeezed between the vertical and the oblique asymptote. And if you were to graph this yourself and you zoom in, you'll see that it will be below the x-axis between negative infinity and negative 3 over 2, above between negative 3 over 2 and 0, below again between 0 and 5 over 2, and finally above the x-axis from 5 over 2 to positive infinity. So that would be how you would graph a rational function.